Okay, it's time to talk about buffer solutions, and pretty much buffer solutions is a practical application of the acid-base equilibrium because, well, we are talking about pH. pH is probably the main thing when we are working with acids and bases, and buffer solutions are mixtures that will help you control the pH. And by controlling, you mean if you want to have the pH at a certain value with not much variation, that's when you use a buffer solution. Okay, so they are substances that will resist the changes in pH whenever an acid or a base is added. Well, if it's something that it doesn't change the pH, then you don't have anything to worry. There are two main components on any buffer solution. You need here significant amounts, a significant concentration. You want to resist changes in pH. The more you have of that acid or base, the more resistant to change you will be. Think in terms of, I don't know, an emergency fund. The larger that emergency fund it is, the longer you can subsisting without employment, so to speak. It's a dramatic example, but the buffer, it's kind of on the same line of thinking. It's something that prevents changes in pH, and the more concentrated you have that buffer, the better it would be at controlling pH. So what do you need for a buffer solution? You need a weak acid and its conjugate base. Is not the only type that you have. If you have a weak acid and a conjugate base, then we are talking about probably an acid buffer. And if you have a weak base and its conjugate acid, then probably we are talking about a basic buffer. And by this we mean we are talking about buffers that are below a pH of 7, and by basic we mean buffers that are above 7. Is that all the time without a section? Well, not necessarily. So it depends on the combination of substances that you have there. Examples of buffer in nature, well, blood. Well, it's a mixture of carbonate. It's a carbonate buffer. Let's put it this way. It's a carbonate buffer that controls the pH in certain range of pH. Okay? So how do you do a buffer solution? Well, you have to mix. Usually you mix equal amounts, not equal amounts, but significant amounts of the weak acid and the conjugate base. What concentration you need of each one? Well, it depends on what the pH you need. So the working and playing with those proportions between the acid and the conjugate base, or the base and the conjugate acid, then you can select the pH in which you want to work. So how does the acid buffer behave? So let's say, for example, in this case, we have the acid. Let's highlight the components of the buffer, right? So this is the weak acid, and this is the conjugate base, right? So this is actually your buffer system. And here we have a strong base, right? This is a strong base. So if you add that base to the buffer solution, then the base will react with the acid and then will give you the conjugate base for the acid. Okay, this is a neutralization reaction. Okay, and as such, if you still have leftover acid after the reaction, then the change in pH would be rather small. How small is small? Well, it depends on the concentration of the acid, and it depends on how much base you add. And that change in pH, it's also compared to what would be that change in pH if you were adding just the base. So we will have an example later on. Okay? So this was a acidic solution, right? So now, how does the buffer actually works? So Now, if we're adding acid, okay, so in the first case, we were adding base, right? In the second case, we are adding a strong acid. And once again, we have our buffer system here. So is the acetate plus the acetic acid. Now, the situation here is that if you are adding acid, then the acid will react with the conjugate base of the buffer. Okay, so in the first case, the base was reacting with the acid. In this case, the strong acid is reacting with the conjugate base, and then you are regenerating the acid. Okay, as long as you have significant amounts of both the acid and the conjugate base, you will have a small change in pH. So, and this is the mechanism of action of a buffer. By reacting with the acid that you're adding or the base that you're adding, you are somehow controlling those changes in pH from not being too large in change. Okay. Now, we are talking about the base, right? So, think in these terms. Okay, whenever we are having these solutions, because this is an acid buffer that now we are using a generic equation and you are adding the base. You know what? Let's use. Yeah, let's use this. Okay. So think this in terms of Le Chatelier's principle. Okay, we are either adding or we are removing stuff from the reaction. And probably, you know what, let's use this equation. HA goes to A, not A plus, A minus plus H plus, right? So what happens if to this reaction, let's erase that for a moment. Let's erase this for a moment. I need more space. So let's think that for a moment we are adding HCl to this reaction. What is going to happen? Okay, you are adding, if we think in terms of HCl, we are adding H plus Cl minus, right? If we look from the point of view of Le Chatelier's principle, adding acid is increasing the concentration of that. What is the response to the equilibrium? The response to the equilibrium, the response of the equilibrium is to shift to the left. If you increase the concentration of the H plus here, you will move that, or you're going to shift that equilibrium in a way that will decrease that concentration of added protons. So you will consume products and you will generate reactants. Okay, so if we see it from the point of view of the concentrations here, so the concentration of HA will increase, the concentration of A minus will decrease. Okay, by adding acid. Now the opposite is true if you are adding base. So let's again erase here so that I need a little more space. So let's use the same equilibrium, right? So in the same equilibrium, we have HA that goes to H plus A minus. What happens now if we add sodium hydroxide? Okay, so sodium hydroxide will give you Na plus OH minus. this OH minus will react with the proton. Okay, so adding the base will make the concentration of H plus to go down. So if you decrease, it's equivalent to removing H plus, let's put it that way. So adding base is equivalent to remove H plus, therefore the equilibrium will respond. How will the equilibrium respond? By shifting to the right, okay, favoring the products, making the concentration of A minus increase and the concentration of HA decrease. Okay, so you can use Le Chatelier's to explain how the buffer is acting, and or you can use stoichiometry to say, well, the sodium hydroxide is reacting with the acid. Either way, it's just fine. So likewise, now we have a situation here in which we have our equilibrium again, right? This is the generic equilibrium that we've been talking. So we see what happens if you add acid, we see what happens if you add base. Now we have another situation here in which what happens if we add more A minus? Okay, what happens if we increase the concentration of A minus? How would the equilibrium respond? So if you increase A minus, then your equilibrium will go to the left. So the equilibrium will respond in such a way that you will increase the concentration of HA, and because you are going to the left, then the concentration of H3O plus goes down. You are consuming the H3O plus to generate more of the acid. So that happens when you add more of the conjugate base. And this is an important concept to understand, the common ion effect. Okay, it will happen here in these equilibriums, in acid-base equilibrium, and it's going to be really important when we talk about precipitation, which is going to be later on. Okay, so this is, again, we are using Le Chatelier's to explain what happens to the equilibrium depending on what changes you make to the equilibrium. In this case, if you add more of the conjugate base. If you are more of the conjugate acid, then you might expect the equilibrium will shift to the right. Okay, so here it's just a graphical example of what happens when you have these two situations. In one case, you have only acid. In this case, you have only the conjugate base. Okay, so you are with the acid, you are at 290, pH 290. With only the base, you have pH of 890. When you mix equal amounts, equal concentrations of the acid, then you are somewhere in between. You are not down the acid or being as acid as having only the acid, or as basic as having only the conjugate base. So you are somewhere in between, and that's exactly where the buffer will work. So a buffer that only contains the acid or a buffer that only contains the conjugate base will not work as a buffer. It might work in one way, but it will not work in the other way. It will not have that much power controlling pH. So the best use of a buffer is when you have probably about the same concentration of both the acid and the conjugate base. But it also depends on what pH you are working. Not all with the time the pKa of the acid will land exactly at the pH that you need. So that being said, how do you calculate pH when you have a buffer solution? And remember, buffer solution implies that you have both the acid and the conjugate base. So in this particular case, this is acetic acid. And you know what? One of the things that we need to know is the acidity constant for the acetic acid. So Ka is 1.8 10 to the negative 5. And this is acetic acid, right? So we don't really need to write everything for acetic acid. Once we have the acidity constant, then that we can use a generic acid. So let's forget about this, and let's just say that's HA. And let's forget about this, and then we say this is A minus. So our equilibrium is HA goes to A minus plus H plus. Okay, let's keep it simple. And guess what? You didn't see that coming, did you? In the ICE table. Okay, what is the initial condition? The initial condition is that you have 0.1 molar of the acid and you have 0.1 molar of the conjugate base, and well, we are assuming there is nothing at the beginning. Okay, so the concentration of H plus is 0, so the equilibrium will respond to generate more of that H plus, therefore the change for the acid is minus X. The change for the base, based on the position on the equilibrium, is going to be plus X. And then the change for hydrogen for the H plus is going to be also plus X. So at the end you will get 0.1 minus X, 0.1 plus X, and X. So Ka, which is the product A minus times concentration of A minus times concentration of H plus over concentration of HA, becomes X times 0.1 minus plus X over 0.1 minus X. Now we have an interesting situation here, because if you remember, we have this cool thing that we call X is small assumption, that, well, give you a nice break when doing these calculations, because it could get really ugly if you have to solve that as a quadratic equation. But for X equal it's small, we have to compare 1.8 10 to the negative 5 versus 0.1. And I see that there are 4 orders of magnitude, the difference between the concentration and the constant, so we are safe. We can assume that this is valid. Okay, that means this X and this X goes away, so Ka is equal to X times 0.1 over 0.1, and guess what? They cancel. Ka is equal to X equal to 1.8 10 to the negative 5. This is the concentration of H plus. Therefore, the pH is minus the log of 1.8 10 to the minus 5, and this is equal to 474. Okay? Now, what if you have different concentrations, right? This is still HA, this is still A minus, Ka is still 1.8 10 to the negative 5. The ICE table is pretty much the same. HA goes to A minus plus H plus. Except that for the acid now we have 0.2 is the initial condition. We have 0.1 of the base, 0 for H plus, minus X plus X plus X. Here we end up with 0.2 minus X, 0.1 plus X, and X. Ka is equal X times 0.1 plus X over 0.2 minus X. The concentrations are still pretty high compared to the acidity constant, so we can pretty much keep our assumption, and then Ka is equal to 1/2 of X because of these two numbers here, which makes X equal to 2 times Ka, and that's equal to 3.6 10 to the negative 5. So pH now is equal to minus log of that concentration, 3.6 10 to the negative 5, and this is equal to 467. Now remember, in the previous case, we had equal concentrations of the acid and the conjugate base, and the pH was 474. Now you increase the concentration of the acid. Okay, you have twice as much acid than conjugate base, and your pH dropped a little bit. It went from 474 to 467, which is not such a big change. So you can say, well, you are kind of doing a good job controlling the pH there. Now we can do this, or we can do something a little easier. Okay, because if we think about this, what is Ka, right? Ka is A minus H plus over HA, right? So how about we do this crazy thing? How about we apply minus log to the whole thing? So we obtain minus log of Ka. Because of properties of the logarithm, I'm gonna break down this into minus log of A minus over HA minus log of H plus. If I do that, then this is pKa, this is pH. And if we rearrange this equation, we end up with this equation that we have right here. It doesn't matter what the acid is, it doesn't matter what the conjugate base is, you can always use this equation. Okay, remember this is a positive sign here, and then you have base on top, acid bottom. Okay, and it's something that you can really use to calculate the pH for buffers, because it makes the calculation even simpler. This assumes that the X is small approximation is valid. Okay, if it's not valid, and trust me, I'm gonna put you something that you can always assume that. There is no point in going further than that. So you can use the Henderson-Hasselbalch equation for almost every situation working with buffers. So let's see an example. Okay, so we have the pH of a buffer solution that is 0.050 molar in benzoic acid. And we have the structures here, and you know what? That's probably, unless you are going to calculate the molar mass, that's the most useless thing to use in buffers or in acid-base equilibrium, because you can always say that is HA. The only thing that you care about that is an acid, and the benzoate is your conjugate base. That's all you need to know. Out of this information, you get that the concentration of the acid is 0.050. The concentration of the base is 0.150. And Ka is 6.5 10 to the negative 5. Okay? We need to convert this number. pKa is minus log of 6.5 10 to the negative 5, which is 419. Okay, so now simply pH is going to be pKa plus log of A minus over HA, and this is 419 plus log of, the base is 0.150 and the acid is 0.050, and at the end we obtain 467. So using the Henderson-Hasselbalch equation, it's almost as if you have already done the ice table and all that stuff, and you derive the final equation that you get out of the ice table. That's pretty much what the Henderson-Hasselbalch equation is. But that means you just apply the equation directly to your situation, the buffer that you have, using the concentrations of the acid and the base that you have at the moment. Okay, so the pH here is 467. Now, if you have a base, preparing a basic buffer is not different from preparing an acid buffer. You will need significant amounts of the base and the conjugate acid. However, there is a special consideration that we make here, because when you're working with these buffers, the basic buffer, whenever you look at tables of constant, the pKa's of everything are more frequently published than the basicity constants. Okay, so that means you may find the Kb for NH3, but you will also find reported the Ka for NH4 plus. Okay, and that's okay. For many bases, you will not find Kb, but you will find Ka for the conjugate acid for that base. So that means that it would be a good practice if, instead of looking at the acid-base equilibrium from the point of view of the base, you see it from the point of view of the conjugate acid. And this is what we have here. This is the conjugate acid, and this is your base. But we are just written this equation from the point of view of an acid equilibrium, not the base equilibrium. Because, I mean, you can derive the Henderson-Heisenberg equation to calculate pOH, but most of the time, let's face it, you are being asked to calculate pH, so let's put everything in terms of pH, and that's what we are trying to do here by looking at the base equilibrium from the point of view of the conjugate acid. Okay? So that means that we have to make another calculation here, right? Because this is the acid equilibrium for the conjugate acid, and this is Ka for that, right? But what is Kb? Kb is going to be BH plus OH minus over B, right? And what happens here is that, well, if you look at these two expressions, it looks there is something familiar there, right? So you have both the base and the conjugate acid there. How about we multiply Ka times Kb? If we have Ka times Kb, then you end up with B times, let's use H plus, over BH plus times BH plus OH minus over B, just the base. And here what happens, these cancel with this cancel with this, and then you are left off with the product of H plus times OH minus. And what is that? That is Kw. So for any conjugate pair, okay, and let me stress this, for conjugate pairs, only, okay, let's stress that, I cannot stress that enough. For conjugate pairs only, Ka times Kb is equal to Kw. Okay, if you have the acid constant for an acid, okay, the base constant for the conjugate base, you can obtain it from that expression. And vice versa if you have the case of a base and the conjugate acid. So in the next example, we have just that. Okay? So the pKb here, okay, and of course, we can do something similar if remember, if Ka times Kb is 10 to the negative 14, if we apply minus log at both sides of the reaction, we'll end up with this expression here. pKa plus pKb is equal 14, similar to pH, pOH thing, okay? But just using the acidity and the basicity constant in this case. So if we have a pKb of 475, this pKb is for ammonia. But if we want to use the Henderson-Hasselbalch equation to calculate pH, then the pH is going to be the pKa plus log of NH3 over NH4, the base over the acid. We have the concentration of each one of those, okay? But this pKa refers specifically to ammonia, to ammonium ion. Okay, that's why we have to go through all of these. We subtract 475, which is the pKb, from 14, and then you obtain Ka. This is Ka. Okay, and this concentration is 0.50. This concentration is 0.20, and the pKa is 925, which is what you have right there. Okay, and you end up with a pH equal to 965. Okay, so once again, this is a basic buffer from the point of view that you are using a base and the conjugate acid, but you are treating the whole buffer situation from the point of view of the conjugate acid. Why? Because it's going to be easier. Why easier? You always have to calculate pH. So let's use just a Henderson-Hasselbalch equation calculating pH. You have the relationship between Ka and Kb. You can perfectly calculate one from the other, and then you are not potentially messing around with two different equations that are calculating two different things. So make your life easier. Let's treat every single buffer acid-base equilibrium as an acid, and then just work with the pKa's. Okay? So graphically, what happens when you add acid or base to a buffer? And this is, now we are gonna enter into the calculation. What happens, how good the buffer is at controlling pH. So in this case, as we were saying, in this particular case, here in the center, we are with equal concentration of the acid and the conjugate base, okay? If you add acid, you increase the concentration of you increase the concentration of HA, and you decrease the concentration of A minus. You can say from the point of view that H plus is reacting with A minus, or you can use Le Chatelier's to indicate, well, if you are adding H plus, remember H plus is a product in the acid equilibrium, then you will consume the A minus in order to decrease the concentration of H plus that you are adding. And if in the opposite case, OH minus will consume the acid, okay, so the concentration of the acid will go down and the concentration of the conjugate base will go up. And as long as you have a significant amount, they are changing, but as long as you have a significant amount of each of those substances, then your pH is under control. They will change a little bit, but not as dramatically as if you were adding those acids or bases to pure water. So then what it takes to calculate the change in pH when you add acid or base to this buffer solution? Well, you have two steps here. First, you have to apply stoichiometry. You have to apply stoichiometry so that you know how much of the acid is being consumed, how much of the base is being consumed. So you need to know what the change is. Okay, and then once you establish what the changes are, and yes, changes, right? You are thinking about an ice table here as well. And then you move into the equilibrium calculation. Hopefully, because we are working with buffer, hopefully we will always be able to use the Henderson-Heisenberg equation. Okay? So here is the situation. We have 1 liter of buffer, okay? And this buffer contains 0.1 moles of acid and 0.1 moles of the conjugate base. pKa is 474. Because the concentrations are equal, if we write the Henderson-Heisenberg equation, pH equals pKa plus log of A minus over HA, okay? If A minus is equal to HA, which is the case here, then they cancel each other and you end up with logarithm of 1, which is 0. Okay, if they are equal, then pH equals pKa. So in this case, it's 474 because the situation is that you have equal amounts of the acid and the conjugate base. Now the situation is that you add 0.10 moles of solid sodium hydroxide. Okay, so and here we are just at the mole level, right? We are not really working with concentrations right now. I will leave that for later, but we can do the stoichiometry just at the mole level right now, right? So the reaction is HA plus NaOH goes to A minus plus H2O plus Na, and let's keep the Na. It's there, but it doesn't really matter for us right now. These are the main actors. So initially you have 0.1 of HA, you added 0.01 of sodium hydroxide, and then you had 0.1 moles of A minus. Correct? So what is the change? Well, the acid and the base will react. I mean, the HA plus Na from sodium hydroxide will react. And the concentration of the amount of the base is smaller, so it will be completely consumed, 0.01. And because the stoichiometry is 1:1, if you consume the acid, then the change for the acid is 0.01, and you generate the base, so for the base the concentration is plus 0.01. At the end, this change means that you have nothing left of the sodium hydroxide. You decrease the concentration of the acid by 0.01, so you end up with 0.09, and you increase the concentration of the conjugate base by 0.01, and now it's 0.11. Okay, let me erase those here because we don't need them. So pH is going to be equal to 474. Now is the new situation, plus the log of the base, which is 0.11, divided by 0.09. And here is 483. So your pH, by adding that amount of solid sodium hydroxide, went from 474 to 483. Okay, so that's what the buffer is doing in controlling the pH. Now, if you didn't have any buffer, if it was pure water, and let's create another box here. If it was pure water, okay, you have a volume of 1 liter. You have hydroxide equal to 0.01, so the concentration of OH minus would be 0.01 molar, right? Here, the pOH would be minus log of 0.01, which is 2. The pH is, the pH would be 14 minus 2 equal 12. And it's pure water, right? The pH of pure water is equal to 7. Just adding that amount of sodium hydroxide would change the pH from 7 to 12 in pure water. A buffer, you have a buffer, you control the pH at 474, it just changed less than 0.10 units, 0.1 unit of pH. Okay, so that's the power of a buffer in controlling pH. So what if we have the same example? So it's 1 liter, you have 0.1 moles of the acid and 0.1 moles of the base. But in this case, we're adding acid. But we are adding and not giving you the amount of acid in moles, and giving you and adding 30 milliliters of 1 molar HCl. So, question, how many moles of HCl? Well, we need to convert this to liters. 0.030 liters times 1 mole per liter of HCl, so you are adding actually 0.030 moles of HCl. Now in this particular case, because you are adding acid, then we should write the reaction as HCl plus A minus that goes to HA plus Cl minus. And we are not interested in the Cl minus. So initially you have 0.03 of HCl, you have 0.1 of the conjugate base, you have 0.1 of the acid, and we don't care about the chloride. The concentration of HCl is smaller than any of the, well, particularly the conjugate base. So the HCl is completely consumed, so the change is 0.03. The conjugate base is also being consumed, so the change is 0.03. And the change for the acid is plus 0.03. So at equilibrium, you will find 0 of HCl. You will find 0.07 of the conjugate base, and you will find 0.13 of the acid. And then your pH is going to be pKa plus log A minus over HA. This is equal to 474 plus log of 0.07 divided by 0.13, and this is equal to 447. Okay, the change in pH by adding acid, 474 to 447. Yes, it's a pH slightly more acidic, but the change is not as large as if you have pure water. So that's the usefulness of the buffer, and this is how you work in terms of what the change in pH. So sometimes one question that I may ask you is not what is the final pH, but what is the change in pH? Sorry. Let's use a different color, shall we? What if I ask you what is the change in pH? Well, the change in pH would be final minus initial. 447 minus 474, and this is 0.27 minus 0.27. It means that the pH decreased by 0.27 units. Okay? So that's it for buffers. I think there is one more thing that we have to discuss about buffers, and that is buffer effectiveness. But in terms of calculation, this is pretty much it.